Compression so far only, right? So compression is only one part of the problem. Okay, in order to do good communications, you need two parts, right? You need good compression so that the file size is small. That's obvious. The bandwidth is low, but you also need the actual communication part, right? How do you actually send those information also? How do you send a bit stream over? So today we take a quick look at communications of images and video over our very popular communication channels. Okay, so we have several popular communication channels. Right? We can have a dedicated line. We can have the internet protocol, the IP networks. Okay, or we can have a wireless communication. Okay, and obviously we're working with images and video. It's a lot more data intensive, right? Bandwidth requirement is a lot larger than your regular email, right? Communication of an email or text is pretty easy to do, okay? But communications of huge images and video files or sequences or streams are not so easy to do, okay? And it turns out that, so with one big signal, we already have a problem. Voice over IP works pretty well, but it takes a long time for voice over IP to really establish itself. Okay? The idea has been around for ages, but it takes a long time for people to figure out all the details, make sure that the system works the way it is, and then introduce to the market. Now voice over IP becomes a very popular tool, so a very low cost, effective solution for voice communication, right? And hopefully we would like to do the same thing for images and video. But so it gives you an idea that in order to do this, you're not going to see the result immediately. It's going to take some time, okay, for it to happen. But the key is we position ourselves in such a way so that when it's ready for prime time, we're right there in the middle of it, right? That's it. We'll talk a little bit about network multimedia. We'll talk quickly about some of the network types and examples, and we focus on IP networks. It's very popular nowadays, and so we're going to use the internet. The IP setup, internet protocol networks to transmit these images and videos. We talk a little bit about source versus channel coding. Okay, this is the protection of velocity communication channels. And if we have time, we will spend a lot of time on error resilience. That's the entire idea. Okay, most of the communications channel that we have. Especially with images and video, we cannot afford to sit there and wait. Okay, most likely we just have to move on with losses and hopefully try to cover up our error as much as possible. Okay. Now, so the internet has many different modules. We can have major enterprise, like large companies and governments do it. There are small businesses. Telecommuters using wireless cell phones. There will be home offices, consumers using ADSL, cable modem, PSTN, dial-up service. Okay. So there are many different types of classes of users sharing the same big block that we call the internet. All the fiber optics cables connections that lay down in the ground. Okay. Now, what are the considerations for multimedia? So this is the difference between multimedia communications and email communications, or text and HTML communications. Right? We need some degree of error resilience. Okay, we have a lot of redundancies in the images and videos, so hopefully we will be able to take advantage of that. Okay, with text and emails, it's harder to have that type of correlation. Okay, so there are a lot of these error resilience techniques seem to work much better with visual data rather than with text data. The bandwidth requirements is huge. Okay, so that's another difference. We will have to struggle with two types of bandwidth requirement: the constant bitrate requirement and the variable bitrate requirement. For video, which one do you think is better? Should we do constant bitrate or should we do variable bitrate? Variable bitrate, right? Why? Our video frames are not uniformly distributed in any sense, right? Sometimes we don't have motions, so the bitrate will be low. Sometimes we have a lot of motion, the bitrate will be high. And if we insist on doing constant bit rates, like the HTML, the text communications, we wouldn't be able to deliver constant quality, right? We just have to sacrifice quality for bit rate. And that's not what we want to do. We want to watch videos with relatively constant quality. We don't want the flickering effect, right? So, and there's a problem between symmetrical and asymmetrical, meaning should we make both encoder decoder having the same complexity or different complexity? So obviously, we are sitting right here because our decoder are typically having a lot lower complexity than the encoder. Okay, for most practical cases, that is good. Okay, but as we mentioned yesterday with distributed coding, there's some setup that maybe you want a symmetrical setup. Okay, now the quality of service is another problem. We have to make sure. Okay, so these are the type of errors that would affect the quality of service. Okay, so you will have delay in the network, you have packet loss in the network, you have bit error rates. So most of the time when you guys work with channel coding, we are concerned about bit error rates. Okay, but there's one more level up. It's the packet loss level. You're losing busty type of loss. That you lose the entire chunk of data rather than losing 1 or 2 bits. Okay, so that is the type of the packet loss and the delay jitter give you the bus error rate, the bus error length that we also have to worry about. One more, real-time constraints. In video, we have to keep up with the frame rates. Okay, if you set up with 15 frames per second, 24 frames per second, you have to try your best to keep up with the real-time constraint. Okay, nobody wants to stop in the middle of the video and say, okay, we're going to take a break. Okay, when I'm paying as a paying customer, I click on a button to watch something over the web. I demand to watch a video from beginning to end without any interruption. Okay? That is a different course. Okay, we don't have time to attack that problem yet. Okay, and finally, as engineers, we are very worried about cost all the time. Okay? We're very conscious about the cost of the system, the cost of implementation, the cost of deployment. Okay, so let's trace back and take a look at what type of networks is available to us if we want to communicate image and video over a certain communication channel. Okay. So the first type of networks that becomes very popular is circuit switch network. Okay, the principle is this: several connections are time multiplexed over one link. Okay, and a dedicated circuit is established during the complete durations of the connection. So this is basically our old telephone network. This is how we communicate with the regular telephone, landline telephone. Okay, when somebody pick up the phone, dial the numbers. Okay, it will set up a dedicated circuit. The translation table here will make a connection from here to here. And this is at the operator. Okay, so they're going to make a connection here to here, and that's how this guy can talk to this guy. Okay, and how do we share the entire copper line? Well, we share by time multiplexing. Okay, so from 0 to from integer n to integer n plus 5 seconds. The first guy is using the line, okay, and then on the second half, the second user is sharing the lines. Okay, so we time multiplex in this fashion. Okay, so that's one way to accommodate more people. So this is some of the features. Is certainly with a dedicated line, you can afford to have a constant bit rate, right? You have a dedicated line, okay? You own the line, so you can do whatever you want to do with it, okay? And it depends on the implementations. You get a certain amount of bit rate. Okay, so for example, a 64 kilobits per second PCM channel, postcode modulation channel. Okay, so this certainly has very short transmission delay, and it doesn't have any small jitter delay. Okay, you own the line, so you just keep on communicating. There's no problem. There's no interruption. Okay, so that is the public switch telephone network or plain old telephone service, and some of the earlier internet connection is based on this technology. For example, ISDN. Okay. Now, so this is certainly suitable for real-time application that requires constant bandwidth. Okay. For example, you can do audio streaming, not compressed audio, but just raw audio streaming, right? Take directly from the CD, communicate over the line. Okay. You have constant bit rate. Every second, you have to send 44,100 samples. Each sample 16 bits, so on and so forth. Okay. And maybe it is also good for something with pretty much constant bitrate compressed video. For example, when we do video conferences, okay, just one camera here, focus on the room. Okay, the bitrate is pretty constant. Right? People are moving, but nobody is moving in a drastic fashion, right? There would be no camera panning. As we see yesterday, panning gives you a lot of bit rate, right? A lot of motion vectors, a lot of residues, right? But if you have a fixed camera and not too many object movements, you are pretty close to constant bit rate. So in some cases for video communications, this is actually okay. Okay, and that's how it's being the earliest teleconferencing package or applications actually just use ISDN. Okay, and there's no problem. The resolution might be low, the quality might be low, but it works. So now, this type of network is certainly not efficient for bursty applications. When you download something, when you transfer something, when you prep web browsing, so with circuit switch, you have the constant bit rate like this. And if your bit rate happens to be moving in this fashion, then you're wasting your bandwidth here, right? Because you don't use up your allowable bandwidth, and you are running into trouble here. That's a problem. Okay. So that's why people are more motivated to design something called packet switching networks. Okay, and this is the type of protocol that we're using every day now over the internet. So it's the end-to-end data stream is divided into small little chunk of data called packets. Okay, and these packets are sent over communication channels. Packets from different users can share the same network resources. That's the entire idea. And each packet will use the full length bandwidth, okay, during the time allocation that is allowed for transmission and receiving. Packet travels through the link through packet switches, or also known as routers. Like nodes, intermediate nodes that receive a packet and then send it to another node. Okay, it allows more users to share the networks. Okay, but there are several things that we can get into trouble with this kind of implementations. We need some kind of buffers or queues and require the routers, because there are many people sharing the networks. Many packets from many users can come to a node simultaneously at roughly the same time. So you need a buffer to store all those packets, and then go into the packet headers to figure out who is sending what packets to who, and who has the priority in retransmission. Okay, we're going to talk about this in a few minutes. If the link is busy, then the packets are queued in the buffer, and if the buffer is full, you have this problem. Packets will be dropped. Okay, if the buffer in a certain router is full, it will not accept any more packets coming in. It will be dropped, and then that leads to packet loss. Okay, so the principle is this. This is a typical data packet. It has a header. It has what we call payload or the body. This is where your data stays. Okay, and it has a trailer part. Now, what does the header do? The header has the packet length, the overall length of the entire packet, the packet number or the index of the packet. Okay, this is number 2 out of 10 packets that user A is sending to user B. Okay, it's very intuitive, right? So based on the index, the receiver is going to receive all the packets that involves AB. Based on the index, put all the packets together, concatenating them together into a stream, cut out the header, cut out the trailer, concatenate the body together, and you get back your part. Okay, that's how it works. Now, you have source and destination routing information, or IP information. Okay, so when you hit send, okay, then the IP address of your current computers is going to be stored somewhere in the headers, and the IP address of who you want to send it to will also be stored in the headers. Okay. Now, and it also has synchronization and transmission protocols. Okay. We'll talk about this in a few minutes. Okay. The payload is the body which contains the data to be transmitted. Okay. So, and typically there's no fixed rule on how large, how long, or how short the payload will be. Okay, it's packets varies in size. There's a typical size that the computer likes to pick, but as if we implement our multimedia communication system, we have the flexibility. Okay? We can make the payload. Well, we shouldn't make it too large, okay, because then protection will be difficult. But it's certainly a lot more flexible. Now, the trailer or the footer right here in yellow is some kind of channel code, some kind of redundancy check codes, parity checking codes on the payload, so that you know that the body is received okay or not. Okay, so that's how your email gets to you without any error whatsoever, because it has a lot of redundancy checks, and if problem arises, okay, then it will request a retransmission. Okay, it will request a retransmission. So if you request enough retransmission, eventually the packets will get there, and everything will be okay. So you can have retransmission requests. Okay, and in our internet protocol, we have retransmission. In some of the multimedia streaming protocol, we don't have retransmission. Why is retransmission bad?
Because it's
delay. It's introduced delay. That's the main reason why it's bad. Okay. So some of the features is that your packets have variable length. Okay, it has pretty large transmission delay. There's no warranty. There's no warranty. Okay, the router has somewhat of a random assignment when it comes to transmitting packets going through certain routers. Sometimes, if you want to send a file from Hanoi to Ho Chi Minh City, Sometimes it goes through Huawei, but sometimes, for whatever reason, it might go all the way to the US and back. There's no warranty, okay? So you might have large transmission delay, and you might have large delay jitters. Okay, the delay might not be uniform. Okay, but it's very popular. Our entire internet is working based on these principles. Our local area network communications is based on this principle. Our WAN is working on this principle, so on and so forth. So this is certainly very suitable for applications which require dynamic bandwidth. Okay, some things that has a very busty type of communication in nature. Okay, so but it has problem with delay sensitive applications. Unfortunately, video happens to sit between these. Okay, it requires variable bit rate, so it fits this criteria, but it also violates this requirement. Okay, you need to be delay sensitive. So that is the problem. Now, how about multiplexing? So this demonstrates the sharing, okay, of the resources over packet switching networks. So you can think of this as your queue or your buffer at a certain route. Okay, there are two users, A and B, sharing the same networks. So maybe blue belongs to A and white belongs to B. Okay, those are the packets. So small little chunks of data. They comes into the queue and waiting for the output link. When the output link is ready, this the router statistically multiplexes the packets. Meaning it doesn't do just A, B, A, B, A, B, A, B. It has a certain randomness to it. Okay, so maybe there are roughly over the entire if there are only two person communicating to this routers, then suddenly the percentage of packets blue being sent and the percentage of packet white being sent is roughly the same. Okay, but there can be 2 blue, 3 blues, followed by 1 white, and then followed by another 5 whites. Okay, there's no guarantee that you will have blue, white, blue, white, blue, white. Okay, so the sequence of packets from A and B does not have any fixed head. Okay, and so this will go to another routers, and the entire process is being repeated. Okay, so everywhere it goes, it knows the IP address. Okay, it knows the IP address, so it knows the end result. It's trying to go from A to C. Okay, it just use those as intermediate nodes to get there, because there might not exist a physical link. Okay, a direct link that links A to C or B to C. We have multiple nodes along the way. Okay, so that's why we need a lot of routers, and that's how Cisco makes a lot of money. Now, so packet switching versus circuit switching. Let's do a brief comparison on which one is better. Okay, so packet. All we can say is this: packet switching allows more users to use the network. It's more efficient, okay? Especially for busty type and we can see it from this very simple example. I have a 1 megabits per pixel link, per second link, okay? Each user, when he or she is active, will use up 100 kilobits per second, okay? And they're active 10% of the time. So this is very popular when you're on the web. You click, you read a little bit, and you do another click, right? And while you are doing the click, data, you are active, but while you're reading, you're not active. You're not using the networks, right? So if you have end user with 1 megabits per second links like this, you can see that, and for circuit switching is dedicated, okay? And each will use up 100 kilobits per second. So with 1 megabit per second, you can afford to accommodate 10 users. Okay, time multiplex, share the same line. Okay. Now with packet switching, with 35 users, you can easily compute that the probability of having 10 active users together is less than 0.0004. Okay? Okay, so this is almost as good as circuit switching with only 10 users. Right? Okay, the probability of having more than 10 active users together is very, very low based on this 10% goal. Okay, so then you can afford to accommodate 35 users without any much trouble. Sharing the same physical links. Okay, what about packet loss and packet delay? Packet queue in router buffers. Okay, like this. Queue delay is the type of packets being in the queue and wait for its turn to be transmitted. Okay, so it's waiting in the queue, and there are packets ahead of it. Okay, so the queue delay is indicating that the amount of time that you have to sit in the buffer waiting for your turn. Okay, and then there's packet loss. Okay, this is not really that critical, okay? But this is very, very critical. You can have a lot of packet losses, okay? Based on the fact that, as I said, the packet arrival rate, if it exceeds the output link capability, then the router doesn't know what to do. Okay? If the router receives way too many packets, then it will break down. It will drop a lot of packets. So this is the problem when for example, our digital cell phones now using packet switching too. Okay, so when a lot of people are trying to call in together at the same location, you will overload the buffer, and then call will get dropped. Or too many people trying to access the internet or one website together. Okay, they'll run into trouble as well. Just like so, Yahoo is being hacked by. It's actually very easy to hack Yahoo if you really want to break. You make sure that you synchronize thousands or hundred thousands of computers sending something or downloading something from Yahoo all together at one time. Okay, then you run into this problem immediately. Okay, there will be packet loss. The routers doesn't know what to do. Okay, so the packets being transmitted, there's a delay. Packets queuing introduce another delay. Okay, and the free available buffer driving packets drop. Okay, is another problem that we have to worry about. So these are just delay, but no loss. This is loss. Okay, and whenever you lose something, you have to request retransmission, and that will introduce the retransmission delay, which is huge comparing to this and that. Okay. Now, so what are the type of packet sources of packet delays? Let's take a look at the processing delay. Processing delay is the time that you have to spend to check for the bit errors. Okay, we have the trailer checking on the body, the channel codes checking on the body, the redundancy checks. Okay, so that takes some time to figure out. Okay, that's one. You have to examine the header, okay, to know that, okay, I'm going to send this packet from A to C. So what route should I take? Okay, so you have to examine the headers, and then you have to determine the output link. Should you send it to intermediate node D, or should you send it to intermediate node E? Okay, so things like that are called processing delay. And then there's the queuing delay, which depends on the behaviors of the users. Okay, so the time queuing delay is the time that you have to spend waiting for the output link for transmission, wait for your turns, and the times that you have to spend based on the congestion level of the router. Okay, now there's transmission delay as well, because you have to store and the forward delay. So this is based on the link bandwidth and the packet length. You have to spend a certain amount of time to actually transmit something. Okay, so that's the transmission delay. And there's the propagation delay, which is the physical quantity between the two routers. Okay, so these are typically small. Okay, but it's actually there. So the total node delay between A and B is the summation of these things. The processing delay, the queuing delay, the transmission delay, the propagation delay. Okay, so that's the total delay from one node to the other. So let's have a quick comparison. Circuit switch gives you dedicated connections. This guy, packet switch, does not. This guy, circuit switch requires the call setup. You actually have to punch in the numbers. Okay, this doesn't require a setup. Well, it does, but it's automatic. The computer figures out the IP address, and so you don't really have to worry about it. Bandwidth is, this guy is fixed, this is dynamic. There's a fixed route, dedicated copper line that actually connects your house to your friend's house if you're actually calling. Okay? But here, the question, the answer can be no. Okay? It depends. For example, wireless, it might go all over the place. Okay? Network congestion here is basically the setup time. Once you set up, everything will be okay. Here, you can have congestion anytime, okay? And utilization charge is important for user perspective only, right? So here is based on the time that you actually spend using the networks, and here is based on how many packets or how much data, how much bandwidth that you are using over an amount of time. So let me bypass this and talk about several of these protocols that we actually use for multimedia. So the transmission control protocol, TCP, together with IP, so that's why we have the TCP/IP networks, okay, is the protocol that we use for the internet, okay. The acknowledgement is required for every packet. You need an acknowledgement that yes, I received the packet, okay. Okay? And that is very important. Okay? That's how the email gets there. That's how the HTML file gets there without any problem. Because there is a communication between sender and receiver all the time regarding are my packets okay or not. Okay? And it offers a reliable in-sequence delivery because of all the packet index. So eventually, if you wait enough, everything will get there okay. There's a long latency because of all these acknowledgement and requests of retransmission. Okay? And it's actually connection oriented. Okay? Meaning this IP connecting to that IP is pretty fixed. Okay? Now, for multimedia, people come up with something called user diagram protocol, or UDP, which relax some of the constraints that we have over here. Okay, for example, we have no acknowledgement in UDP. Okay? Basically, UDP promised to offer us the best effort delivery. I'm going to try my best to get your packets there, but there's no warranty. Okay? Based on just statistical behavior. It has a much simpler protocol, and it doesn't have any connection-oriented. Okay. Now, RTP is another protocol that requires that we will use for real time. So it provides timestamp to resolve delay jitter. So it knows exactly. It provides not only the sequence number, but it also gives a timestamp on your packets. Okay, so that you know that what packets is right now waiting somewhere, and what is the type of delay. Okay. It provides payload type information. For example, it tells you what kind of video that you are transmitting. So this is part of the packet headers. Okay? And the payload format adds redundant information to the headers to eliminate data dependency between packets. So hopefully, this is an advanced protocol that tries to eliminate some of the problems with the redundant, with the dependency between your microblocks, for example. It tries to eliminate that redundancy so that if you lose something, the loss will be local and it will not spread out. Okay. So an example of the type of packets that being used for video streaming over the web will look like this. Okay, you have the source destination address, the regular IP address between the two computers. You have the UDP headers. Okay, you have the RTP headers, and then you have the payload, which is your real video stream. And then after that, you still have the trailer, the redundancy checkpoints. So it adds two more layers to the header information. Okay. So in the multimedia communications framework, we have a setup like this. Okay. So we already studied this problem to death, right? We know what K is, what Q is, what E is, what E inverse is, what Q inverse is, what T inverse is. So this is our regular source coder, our regular source decoder. And before, what we did is we connect this point to this point and say, hey, my channel will be okay. Okay? That's not true. That's not true. In practice, your channel will not be okay. Your channel has a lot of problems. So we have to add this guy. We have to add this transport coder, and we have to add this transport decoder. Okay? In the transport coder, you have to do channel coding. So you have to do packetizations, and then you have to do the modulations that you need to transmit. Okay? So packetization means what?
Breaking the video to
exactly, into packets. Okay? Should you break it in a random way? No, you should not. Right? At least you have to go to the end of the marker block. Okay, at least it's easy to decode that way. Right? Imagine you have a packet that starts in the middle of a marker block. That is very difficult to decode, right? I mean, you don't know, then you have to, there's so much redundancy, there's so much dependency that you have to, for the next guy, you need the other one in order to decode this one. Okay, so you don't want to do something like that. You want, so source versus channel coding. We have been talking about source coding for 3 days now, right? So here, maybe I'll just say something real quick about channel coding. So who has experience with channel coding before? Okay, 1, 2, 3, 4. All right, so looks like I have to spend a little bit more time with channel coding. But let me do just a very simple example. There are many types of channel coding techniques. We heard about a few already, right? Low density parity check, okay, low density parity check, LDPC code. We heard about turbo codes, okay. I did mention hamming somewhere, okay. So those are very popular type of channel coding techniques, okay. So the idea of channel coding is to protect error from happening, okay. So to help with error detection, hopefully you can detect error and then maybe recover some of the errors and conceal some of the errors. Okay? So joint source and channel coding is still an active research area, and hopefully we're going to see that that the way channel coding works is actually very different from the way source coding works. Okay? In source coding, we take away redundancy. In channel coding, we add redundancy back in. Okay, it doesn't make any intuitive sense, but the type of redundancy that we add in for channel coding is very different from the type of redundancy that we take out from source coding. You add in very structured type of redundancy. Okay, you add your own redundancy, so you know exactly how it behaves. Okay. We take away redundancy from the source, okay, but we don't really know exactly what type of redundancy it is, okay. We only do transform, we throw away the small guys, but that's about it. We don't really have very fine control, okay. Now, so the word error resilience means any techniques that protect yourself from transmission error. Okay, error resilience means you are trying to come up with techniques to deal with error and make sure that you're robust with respect to error. Okay, so if you do multimedia over unreliable channels, for example, wireless, okay, it has a lot of problems. Okay, and even with internet, it has quite a bit of problems. Okay, not as much as wireless, of course, but still. Okay, so these are the type of unreliable channels that we have to worry about. The transmission errors in communications typically comes from two sources. Number one, random bit error. Random bit error means you either have a bit inversion, bit insertion, or bit deletion. Okay? You get a bit that wipe out completely, or you get an extra bit somewhere in your data, or you have a 0 is turned into 1, or 1 turns into a 0. Okay. So typically this is very common. It's not very common to have that, because typically we have time windows, okay, that specify for bits. Okay. So bit inversion is very popular, and that's what we're trying to do in the next few slides, trying to protect ourselves from that problem. Now, we have bursty error. Bursty error is the packet loss that we just talked about. You can lose the entire packet because the router determines that, hey, I don't have enough buffer in my queue, so I cannot accept you. So that is the type of bursty error that we have to worry about. So error control goal and techniques is to overcome the effect of errors, such that packet loss, such as packet loss, such as bit errors, so that you will be a lot more robust over a lossy communication. And these are the type of error control techniques that we will investigate. The easiest one of all, already being implemented in our internet protocol, is retransmission. Okay? So, if you check everything and discover that you have a problem, you call up the other guy and say, hey, send me that packet again. Okay? Well, you pay the price for the long delay jitter, but it's, if you're willing to wait, everything will be okay. Another part of error control is called forward error correction, which is the channel coding that you are familiar with. Error concealment is the techniques that allows error to happen, but rely on what you receive to correct the errors. So for example, you might lose a block somewhere in the middle of your video. Okay, how do you do concealment? Any idea?
Interpolation.
Yeah, you use interpolation. That's good. Interpolation in what? Temporal or spatial?
Both of them.
Yeah, can use both. Okay, in video, most likely temporal will work better because there's a lot more correlation in time. But if the block happens to be an intra-block, for example, then you have to use spatial interpolation, right? So it's very intuitive, but it works very, very well because a lot of times video moves by so fast, right? And if you just do a decent job, the end user will not be able to detect any loss in the bit stream. Now, if you watch error resilient coding means advanced techniques that outside of retransmission, channel coding, and error concealment that help. For example, you might overprotect the header. You might overprotect the header, or you might overprotect the motion vectors. Right? They are more important than the residue. Okay? So those are the type of error resilient coding scheme. So there are two types of error recoveries. There are perfect recovery, and there's lossy recovery. So perfect recovery means that you try to, for example, channel coding or retransmission will provide perfect recovery within the constraint that you meet. Okay? That means you'll be able to get your data back without any problem. But the type of lossy recovery is, for example, concealment is a type of lossy recovery. Okay? You allow loss to happen. You know that the decoded result will not be exactly the same as the transmitted result, but hey, it's okay. Basically, if the error is not so perceptible to the human visual system, we're okay. So an error example is like this. This is a video frames, okay? These are called slides, which is just a group of macro blocks that encode together. Okay. Now, slice means that there is no relationship between this slice and the next. Meaning, right here, okay, if I have any type of prediction across, I don't predict gray from white. I don't predict gray from white. So I make sure that make sure that gray has nothing to do with white. Okay, so that if I lose white, I can just start decoding from here without having a problem. Okay, so that's the entire idea of having slice. Okay, so these different colors indicate different slice, and then I have an error. Okay, this error will lead to more errors. Okay, for example, if you do Huffman coding, right? You do Huffman decoding, and suddenly a bit got flipped. 1 becomes 0. Will you decode it right? No. And what about the rest? There's no warranty, okay, that the rest will be okay. You have to wait for the next synchronization point, okay, or the next symbols or something in order for you to resynchronize. So there, if you have a slice that goes from here to here, okay, and you make an error here, for example, in red, okay, then the rest is very likely to be corrupted as well. Okay, that's why the loss comes from here. And then everything will be okay here because this has nothing to do with that. Okay, so you resynchronize. Okay, but then you make another type of errors. This type of errors, okay, there might be a very, this slice is short, right? So you make an error here and you only propagate up until this point and you get resynchronized. Okay, so having smaller slice will certainly help. Okay, but why don't we try to make all of our slices very, very small?
Because we are so supposed to be not compressed.
Exactly. You will pay a price in compression efficiency. Okay? Making these slides independent comes at a cost. You're not allowed to do prediction across the slides, so you pay a price for compression. So this is the trade-off between compression efficiency and communication robustness. Yeah. Okay, so that's life. Okay. Now, error can propagate. Okay, so here I only show one frame. What happens to the next frame that comes after this? Can there be error? Why? When the next frame comes, okay, I want to do motion estimation. Which one do I use? I use this one. This one has error. Okay, so then error will propagate to the next frame. Error will propagate to the next frame after that. Error will propagate everywhere until you do intra-coding. Okay, that's why we have a lot of intra-coding sometimes, because intra-coding helps us resynchronize, eliminate all these propagations of motion, and allow us to resynchronize ourselves. So that's why in MPEG, one of the reason why they have I-frame, which is intra-coded frame, one every 10, 12, 15 frames or so, is because of communication robustness. Another reason for having I-frames is for
reduce the residue, accumulate.
Yeah, but that's part of this problem. Another reason for I-frames is for random access. Okay, you want to fast forward, right? Do you know how fast forward works in your DVD? Just decode the I-frame. Just decode the I-frame, right? That's fast forward. Okay, or go backward. Just decode the I-frame in the back. Okay. So let me bypass and talk about retransmission. So the requirement of retransmission is there's a feedback channel between receiver and senders. Every packet will have an acknowledgement of some kind. Yes, the packet gets the OK, or no, the packet doesn't get the OK. If the packet doesn't get the OK, you request a retransmission. If the packets get the OK, acknowledgement being sent, the sender receives the acknowledgement and then eliminate that packets from the list of packets being sent. Okay, so this is the advantage is that it's easy to adapt to changing channel conditions, and it offers lossless communications over lossy communication channels, but there can be a lot of problems. For example, the latency not applicable when feedback channel is not available. For example, in broadcasting is one way. There's no sending back to the satellites what you receive or not. Okay, and the effectiveness decreases with increasing channel errors. Okay, so let's move forward to forward error corrections. Forward error correction is is known as channel coding usually, okay, and it's the type of techniques that add redundancy in the back here so that it checks for errors in the yellow. Okay, so this is one of the very popular forward error correction codes is Reed-Solomon codes being used in currently being used in your VCD and your DVDs. Okay, it's the type of codes that it will take me a few, maybe an hour or so to explain. So instead of explaining Reed-Solomon codes, let me explain the simpler one, Hamming code, which is Hamming code is the earliest type of channel coding techniques that being introduced. It's actually the first. Okay, and based on this is the fundamental. It contains all the fundamental of channel codes. So everything that comes, all the linear block code, even that comes after it, is basically a generalization of Hamming coding techniques. Okay. So in Hamming code, I have my message bits, or the bits that I want to send. So M1, M2, M3, M4 are the actual bits that I want to send. The P1, P2, P3 are all parity bits, or the checking bits. Okay? Okay, you know what this does? This is the XOR. XOR means it's a binary addition. Okay, it's binary addition. So 1 plus 1 give you 0, 0 plus 0 give you 0, 1 plus 0 give you 1. Okay, so that's binary additions. But it gives you a bit. Okay, so it doesn't have any carry. Okay, it just does addition once, forget the carry. That's what XOR does. Okay, so I have the P1, P2, and P3. The Hamming encoder look like this: 4 guys coming in, 7 guys coming out. So this is a redundancy type. Okay, this is the inverse of compression, right? In compression, 7 guys come in, 4 coming out, right? So here we add redundancy, and the redundancy is are the P bits right here. So this is called a 4-3. Okay, this is a 4-3 because there's 4 bits here, and then K.
3.
Yeah, right. This is the protection bit. Okay. Now, oh no, I'm sorry. It's the 7. Yeah, 7-4. 7-4. This is the 7-4 Hamming code. Okay. So the way it works is actually very simple. Your message bits are here. Okay. And the way you get P1 is by doing an XOR between the 3 message bits in overlap. So you get P1 by XOR M1, M2, M3. Okay? You get P3 by adding this. You get P2 by getting this. Just adding. Okay? So encoder is really simple. Okay? Now, what do we do for decoding? So before decoding, let me introduce the concept of Hamming distance. Hamming distance is a type of norm, okay, that measures the difference between 2 binary words or 2 binary chunks, okay? So for example, the difference between 01101 and 01100 is just 1 because there's only one differing digit. the difference between this and this is 2 because there are two different digits. This is 0 and this is 1. This is 1 and this is 0. Okay, so this is the Hamming distance. Visually, this is how it works. Okay, for example, in the parity code, suppose that I have my 2 bits, and then this is the redundancy check bits. Okay, then there are 4 possibilities. There are 4 possibilities because I have 2 sending bits, right? So there can be 0, 0, there can be 0, 1, there can be 1, 0, or there can be 1, 1. So these are 4. And then, how do I get the one in red? I just do XOR. So XOR 1, 0 give me 1, XOR 0, 0 give me 0, XOR 1, 1 give me 0, XOR 0, 1 give me 1. Okay, so as the decoder, when I receive 1, 1, 1, I know that I'm in trouble. Because 1, 1, 1 doesn't follow the rule. The rules say, add the first 2, get the last. Okay? I add the first 2, I get 1. So that's, I get 0. I'm not supposed to get 1. So I know there's some error. So that is called error detection. Okay? You know that error happens. But then, how do we correct it? Well, in this case, too bad. There's nothing I can do. Okay? Error might be, this guy might be a 0. That certainly will work. This guy might be a 0. That certainly will work. Or this guy can be a 0. That certainly will work. Okay? So I don't know. It might be those 3. And visually, the error happens because you happen to sit right here. And you don't know where to go because you are equidistant from both of, from all 3 of these perfect codes. Correct? Okay, so let's take it one more step forward. Now, I'm going to try to increase the redundancy. So this is the dumbest redundancy code that I can think of. I will repeat myself. I just repeat myself, okay? I don't do anything, I just repeat myself. So if I have 1, I will repeat 2 times. By the way, this is a very effective communication technique. If you want somebody to, okay, this is how your parents talk to you, right? They just repeat, repeat, repeat. You study well, you study well, you study well, you study well. Okay? They keep on repeating until you get it, okay? That's a very effective communication technique. So this is 1, repeat 2 times. And this is 0, repeat 2 times. So in this case, there are only 2 possible codes. Okay? And if you happen to be right here, you know where you should map yourself to, right? The closest guy. Okay? And if you want to map yourself to here, you actually have to go, the Hamming distance is actually 2. The Hamming distance from here to here is 1. So all the yellow points will get mapped here, and all the green points will get mapped here. So in this case, you correct. Okay? But how many can you correct?
1 bit error.
You can only correct 1 bit. If there are 2 errors in here, you might make an incorrect decoding. Okay, so that's the entire idea behind channel coding. Okay, so and these are the red bits are called redundant parity check bits. So let me go back to the Hamming examples. Okay, so these are the possible perfect code words that you have. Okay, and the minimum Hamming distance from any of them turns out to be 3. Okay, and you can, if you don't believe me, you just go through the table. What is the Hamming distance from this guy to this guy? 3. What about this guy to this guy? Just count the number of ones. 1, 2, 3, 4. 4. From this guy to this guy. This is 4. Okay, from this guy to this guy. If you just go through the entire, exhaustively search the entire list, you will come to the conclusion that the minimum Hamming distance from any of the 3, any of the valid code words will turn out to be 3. In that case, if the distance is 3 apart, if the distance is 3 apart, then you can detect 2 errors, and then you can correct 1, because this guy will go here and this guy will go here. Okay, that's So these are the codes, okay? So just to demonstrate the encoder and how it works, okay? So in the decoder, let's see what happens. The key to decoding is you receive 7 bits, okay? Errors can be anywhere. Error can be anywhere, right? You can make error in the M, you can also make the error in the P, okay? But you have to, inside the circle, there's one thing very fundamental, right? Inside the circle, see, inside the circle, if you do an XOR of all the guys inside the circle, you should always get 0. Okay? Because the way that we do the XOR before, that's the way we generate the codes, right? So inside the circle, you should always have an even number of 1. That's how you know that the code is correct. So this is correct, and this is correct. Okay? So in the decoding, what you do is you receive those 7s and you put it in these circles. Okay? And then you check the circle. You check one circle, you check another circle, you check another circle. If the result turns out to be all 0, so the XOR gives you 0 here, 0 here, 0 here, and everything is okay. Okay? Fine. I really want to demonstrate that. So suppose that P1, which is this guy, let's see, what is P1? P1 is the summation of this guy, right? P2 is the summations of this guy. Okay, so suppose that if you run into this scenario, red circle is okay, blue table is okay, okay? Green circle has some problem. Green circle has some problem. So the answer is that P3 has problem. Okay? So P3 has problem, then that means you just flip it. Okay? And you can verify that here, in this case, the blue one has problem. So flip this guy. The red one has problem. Flip this guy. Now, what about this case? Red circle is okay. Green and blue has problem.
M4.
So
M4. Right? Green and blue has problem. Red is okay. That's how M3 get eliminated. Okay? But green and blue has problem, so that indicates to you that M4 is the culprit. Okay? So then what do you do? Flip M4. Okay? Now, these has no effect on decoded message, right? Because flipping the P doesn't really mean anything. Our goal is to generate the M, not the P's. Okay? Those are the redundant bits. So over here, you can figure yourself out that you have to flip M2. Here you have to flip M1. And then what if all 3 has problem? M3. Flip M3. Okay, so this is how most of the channel coding techniques works. Okay, at least the linear block code. Okay, it works in the same way. Now you can easily think of ways to generalize this, right? You want to make a longer blocks, and there are many different types of redundant bits that you can add in, right? This is only one way. So that's a very active research area in the 60s, so on and so forth. Okay. Now, what if you have 2 bits error?
We will make more mistake when encode.
Well, okay. If we insist on sticking with the scheme, we'll run into a problem. We know that error is there, but we cannot correct it. Okay? Because if I make 2 mistakes, maybe I'm okay. the green circle thinks that it's okay, but it actually has problem. Okay? So we might know that the error, you make 2 mistakes here. The green say that it's okay, the red say that you have some problem, the blue say that you have some problem, but then if you try to flip this guy, you run into a problem. Right? So that is the type in this case, what we have to do is to increase the redundancy. And so that's a trade-off between general error rate and the redundancy that you have to add to protect. Okay. Now, so Read-aloud code is a generalization of Hamming code. So instead of working on the fields of 0 and 1, it works on the field of integers. Okay? So, and it offers better protections. Okay? So basically, for read-aloud code, what happens is you still receive your packet, and it depends on your the behavior of the channel. You decide to have more or less protections, or it depends on what type of data that you are dealing with. For example, for all the motion vectors, you might protect it more than the residue. Okay, so as the designer, we can have all those things available to us. Now, let me bypass this and talk about error concealment. So that is retransmission and channel code allow us to get lossless protections. Okay, within a certain limit, of course, right? Within the channel capacity limit, within the channel error limit, with the combinations of FEC, forward error corrections, and retransmission, we will be able to deal with the losses in our communication channels, right? But then, concealment is another technique that allows you to boost up the communication rate, okay? And because you allow errors to appear, but you would try to go back and correct the error using some kind of interpolation techniques. Okay, so conceal means you want to hide the error. Okay, so an example would be this. You can use spatial interpolation. Okay, now I strongly recommend you. I think we're trying to do this in our MATLAB exercise, but even if we don't assign this problem to you, if you're interested, I strongly recommend you to try this. Okay, it's very easy to simulate this problem. Okay, what you want to do is to take an image, and you divide an image into 8 by 8 blocks. Okay, 8 by 8 blocks because that's our DCT size, right? Okay, and then you make sure that you alternatively lose blocks. You don't lose 2 consecutive blocks, okay? Because losing 2 guys make your interpolation very difficult. Okay? But suppose that you're here. You're missing this blocks right by Leonard's eyes. Okay? What you want to do is to interpolate this black blocks from 1, 2, 3, 4, 5, 6, 7, 8 neighboring blocks.
Average.
Yeah, you can do simple averaging and see what happens. Okay? You can, believe me, you can just do simple averaging and you're going to be able to get, maybe not quite here, but pretty close, 30-something dB. Okay? 30-something dB. So this is, as you can see, I'm throwing a quarter of my information away. Right? I'm throwing a quarter, 25% of my information away. And I'm still okay. Okay? So nobody knows. If there are 30 frames of lambda passing by you, you wouldn't even know that you actually have a lot of errors. This is a lot of errors. Okay? So this is the power of error concealment. Okay? If we do packetization right. So these, see, I have a regular loss because I do packetization right. I make sure that there's no neighboring blocks grouped together into one packet. Okay? So I might lose 1 out of 4 packets. Suppose I have 4 packets covering this lambda image, okay? Then I'm losing 1 out of 4. And I'm still okay. Okay? So that's spatial concealment. Temporal concealment for video is even more powerful. What you did is, you go to the previous frame, and hopefully you have the motion vectors. Okay? If you have the motion vectors, you go to the previous frame, you pull out the correct block, and you just fill in the blank. If you don't have the motion vectors, then what should you do? Just copy the previous block with 0, 0 motion vectors. You have a very good chance that it's going to be okay. You have a very good chance that it will be okay. the probability is with us, not against us in that case. A lot of times, if you do statistical study of the motion vectors in regular regular video streams, guess what motion vectors is most common? 0, 0. Or the copy, okay, is most common. Then after that, the small one, 1, 0, 0, 1, 1, 1. Those are the type of motion vectors that's very popular. Okay, so you can use that. You can make a very intelligent guess on what is missing. Go to the previous frame, copy it over, all that. Okay, so that's temporal concealment. So another type of a little, you can get slightly smarter. Okay, suppose you lose this block, and you lose everything. You lose the residue as well as the motion vectors. What you can do is take a look at the 3 motion vectors here. Okay, and say, well, if I'm here, I should be moving with respect to these guys. So maybe I take the median of these 3, or I take the average of these 3, or something. Okay, and I call that my motion vectors. And then I go to the previous frame. Based on that motion vectors, I pull the block over, fill in the blank. Okay, so that's another type of temporal concealment techniques. Okay. So maybe let's stop here for a break. Okay, quick break, and then we go back. Where to make slides? Yes. Concealment is considered a subset of post-processing techniques. Okay. So concealment is a technique that post-processing means you decode and then you do some processing after you decode. Okay. So certainly that concealment fits in that case, right? You decode and then you determine where the error is and then you try to eliminate the error, so interpolate the errors as well. So there are motion compensated temporal predictions that we just talked about that, right? That's a part of it. That's temporal concealment. There's maximally smooth recovery, which is a part of spatial concealment, right? Interpolation in time. But you want to do it in such a way that it exploit the correlation both in time and in frequency, and you want to make sure that the edges stay sharp. Okay, so it's just a particular case of interpolation, and there's fancier techniques called projection onto convex sets. It's a type of iterative, frame-based iterative. Approach that do smoothing and replacement of data. Okay, that's you can do frequency domain interpolation. For example, you can interpolate the DCT tangent from the data. That's another way of doing things. And you can do recovery of coding modes and motion vectors, like predict from the neighbor or the previous frames. Now, in video coding, we have to worry about 2 things. We don't want loss of synchronization. Okay, the decoder doesn't know what bits correspond to what parameters, and that is very troublesome. Okay, if you don't know what bits belong to what parameters, you will decode the parameters incorrectly, and that will lead to all kinds of problems. Okay, and then error propagation means the decoder state is different from the encoder state, leading to a mismatch. Okay, and then error will propagate. Okay, so this is loss of synchronization mean. Okay, any error in the bit stream. Okay, any error in the bit stream. For example, this one might supposed to be 0. Okay. In the middle of the bit stream, 0 becomes 1, 1 becomes 0, lead to devastating errors. Okay, that means everything is out of whack. Okay, you're not synchronized anymore, and whatever the rest of the way will just there's no warranty that we can say. Okay, that's in the worst case scenario, you lose everything from here on. So we have to discard everything from here on. The solution for this type of problems is to insert resynchronization markers. Okay? So for example, you can have a start code that look like this. Okay? And whenever you see the start code, you restart the decoding process from zero, from the beginning. Okay. Now, one of those start codes might be maybe the beginning of frame code. Okay. So at the beginning of the frames, we have a start code. Okay. This is the starting of a frame. And you can do the same thing with, this is the starting of a slice, or this is the starting of a group of macro blocks. Okay? So these are synchronization markers that we put in the code so that here we can start decoding independently with respect to the previous bits. So that will eliminate some of the error bits, okay? Because if you make a mistake here, error happens to be only from here to here, then you resynchronize, and everything will be okay. So this is in Huffman codes and also in the arithmetic codes that we studied before. We never consider robustness. We never consider the fact that the channel will have communications errors. Okay. So, but now we know that there's communications errors. Then the question is, can we design a code that might not be as optimal as arithmetic code, but at least provide some kind of protection? So for example, a very smart idea is called reversible codes. Okay? So for example, the way you do VLC decoding, you just start here. And you do table lookup or decoding whatever your decoding process is. Okay? And suppose that you decode all the way here and then, oops, I run into trouble. So this is a corrupted segment. This is where loss appears. Okay? Now, if you just use the regular Huffman codes or arithmetic codes, the rest might be history. Okay? You're done. Okay? Loss will come all the way over here. Okay? But then, if you have reversible code, what it means is, if you decode from the left, okay? You run here, run into errors, you say, okay, fine. I'm going to start from the right, and then I go backward. Okay? So I can decode from the left as well as from the right. And that is called reversible PLC. Okay? This way, you can reduce, you can discard less data, okay? And suddenly it comes at a cost. Nothing really comes for free. Okay? It comes at a cost. The cost comes from the fact that you are willing to sacrifice some of the coding efficiency. Because if you just do it the optimal way, like arithmetic coding, it's not going to be reversible. Okay? Or even when you do Huffman, it's not going to be reversible. So an example of the combination of reversible codes and synchronization codes will be like this. There's an error here. There's a synchronization markers here. So from here on, everything will be okay. There's a problem there. Okay. So you you run into a problem right here. So you look for the next marker. You look for the next synchronization markers. You know that's the end of the slice or whatever, and then you work yourself backward. Okay, you work yourself backward all the way, and maybe up here you're still okay up the way until this point. So then you only lost the one in red, and you can still recover the one in blue. Okay. Now an example would be a non-reversible code. Okay, which is this one, and a reversible code, which is this one. Okay, so let's do a comparison. Okay, now in order to be a good code, we need to satisfy what conditions? Prefix conditions, right? Do we satisfy prefix condition here?
Yes.
We're okay with 0, 0. We're okay with 0, 1. We're okay with 1, 1, 0. We're okay with 1, 1. Looks like we satisfied the prefix condition. So this is a pretty reasonable code. Okay, at least it behaves very, very well, and it looks like it has variable length. So maybe we can show that this is not quite as often. It all depends on the probability of 0, the probability of 1, so on and so forth. Okay, but I'm pretty sure that if you design subsequent code from the correct probability, you might perform better than this. Okay, but it's okay. This code has a probability, has a property that when you flip, okay, so take 0, 0, well, the flip is itself. When you take 0, 1, the flip is 1, 0. So that means you can do backward as well as forward, right? Backward as well as forward. Okay. Now, when I reverse the code word, I still have uniquely decodable code. I still have uniquely decodable. Okay. So, what is the properties of the code such that you can satisfy these conditions? I leave it to you to explore. But I just want to say that there exists code like this, okay, that actually can be pretty powerful in terms of error detection and correction. Okay. So whenever you run into trouble going from left to right, you look for the next utilization markers and you work backward from right to left. Now, data partitioning or packetization is another technique that people use all the time to gain robustness in communication. So the bits closely following the resynchronization markers are more likely to be accurate than those farther away. Right? Can we say that? Because it doesn't have that propagation effect, right? Right? The farther you are away from resynchronization markers, you open yourself up to more errors, the type of the type of propagation type of error. Okay? So the idea is to place the most important information where?
After
Near the resynchronization markers. So whenever you, for example, you have a marker plot, which can be treated as a resyn marker, right? Maybe at the beginning of each marker block, we add a resyn marker. Okay? Then I will put the motion vectors here because it's very important. Then followed by less important data, like the residue. Okay? And then I have another resynchronization markers, another motion set of motion vectors here, then the residue, so on and so forth. Okay? So that's another technique that people use. Now, error propagation comes from the fact that you have P frame, which is predicted from I. I means you encode the frame as is. There's no motion. There's no motion estimation. Okay. So when you make an error here, okay, it has devastating effects because you look for motion, you do motion estimation from this frame based on this frame, okay? And if you make an error, then you have this red block, okay, red circle, okay? Now, this P frame is going to be predicted from this one, okay? And the way we do motion estimations, blocks can be overlapped, right? Okay, because we search for windows and we might catch a red corner of some kind, okay? If you catch a red corners, for example, you catch this corner, then you introduce that errors. You introduce that errors, right? And then you go over here, you predict this one from that one, you catch another errors and it expands this way. And then you expand, so if you catch this corner, it expands this way, you catch this corner, it expands this way. So you keep on expanding until an iframe comes. Until the next iframe comes, right? The next iframe comes, iframe is decoded, okay, is encoded by itself. So you decode it as is, it doesn't have any prediction across the frames, so then you resynchronize, and you're happy. Okay, if you watch digital television, you're going to see this a lot. Okay, there might be plots that get lost. Okay. okay? And then it would lead to a whole bunch of other blocks nearby. And then after about a second or so, and everything is okay. Because the next iframe comes. The next iframe comes, okay? That's your savior, okay? Your iframe is very, very nice, especially when your channel has a lot of errors, okay? So that's the type of error we call error propagation, okay? And as you can see, the P frame is already better. Imagine you have B frames. B frame is bi-direction, okay? So you predict it, for example, you predict this one from this and that. You know, that errors can come from a lot of places. Now, how do we limit error propagation? How do we limit error propagation?
Insert smaller iframe.
We insert more iframes. That's one thing to do. Very good. Okay. What if we cannot insert too many iframes? We're limited. The number of iframes are limited. Iframe costs a lot of bits. Okay. Okay. So how can I limit error propagation with P frames?
We introduce some macro block of you.
Yes, we intra-coded macro blocks in P frames. Okay? How do we do that? Remember that we have a threshold, right? Right? We lower the threshold. That means we bias intra-coding. Okay, we lower the threshold. The threshold say if your SAD is above that threshold, you will encode it as intra, because I cannot find a matching block, right? You lower that threshold, and suddenly a whole lot more blocks will become intra-coded. So that helps. Okay, for example, you have frame n with these blue blocks being intra-coded. You have frame n plus 1 with these another set of blue blocks intra-coded. And maybe you can do something even smarter than that. Instead of letting the bit stream behave in a random fashion, you can try to make sure that these blue blocks are not overlapped. Okay? So that is another smart thing to do. So all these things does not involve any fancy mathematics, right? It's based on tremendous amounts of intuitions and understanding of how what is the problem that we have to face, and what kind of innovative idea that you can come up with so that you can solve the problem in a very effective. The encoder, I run into problems. That is another, at the frame level, for example. So you can say that frame 3, if the decoder detects that frame 3 has a problem, okay, and it tells the encoder, then guess what the encoder will do? What is the smart thing? What would a smart encoder do for frame 4?
So make it iframe.
You can make frame 4 iframe, or you can predict frame 4 from who? Frame 2. Right? There's no problem with that. Okay? But that would require something like smart encoder-decoder communication. Right? Okay, so that's one of the things that people actually do. Now, other tactics would be something called scalable video coding. I don't think we spend a lot of time on that. But scalable means that you code video by layers. Okay, so say base 1. Okay, say a layer. The base layer is layer 0 or layer 1. Okay, the first layer is called base because it contains the most vital information of the video. Okay? Then after that, you add the next layer. The addition of layers 1 and layer 2 gives you a much better video. That is called layer coding or scalable coding. Okay? Why does scalable coding help? It prioritizes the video data. Okay? It determines, the smart scalable encoder determines what is the most vital, where is the most vital information, and it put it in the base layer. put it in the base layer, so that you can protect the base layer more. Right? We are the designer. We do whatever we want to do. Right? We can decide that we protect the base layer more, and we protect the next layer less, and then we don't protect the next layer at all. Suppose that you have 3 layers. We protect layer 1 with a lot of redundancy code, with a lot of techniques that we talk about. We protect 2 very little, and 3 we just let it go. If it happens to get there, great. If it doesn't happen to get there, okay. We can just use 1 and 2, okay, for the reconstruction. So protection of the base layer is critical. Other layers are useless if the base layer is lost, because it contains the most vital information. The way you do reconstruction is this. This is the base layer. You do I, P, 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 so intra-coded, P, prediction coded, so on and so forth. So, and then this is the enhancement layer. So the addition of this and that give you a very high-end video. And then you take this and that, get another high-end video. This is the low-end video. Okay? Low-end means lower quality, but it's still watchable. So that's called layer coding. Other techniques is, for example, multiple description. We talked a lot about it already, so maybe I'm gonna go through this very quickly. One very simple way to do multiple decoding in a very effective manner, okay, in practice is this. This is the interleaving idea, okay? All the red blocks are grouped together into group 1. It will be encoded separately, sent through a separate channel. Okay, or a packet. You can think of all the red blocks get grouped together into one packet, or one group of packets. All yellow blocks get grouped together into another packet, or another group of packets. All the green and all the blue likewise, okay? So here I generate 4 descriptions out of 1 image, or 1 frame, okay? Then guess what? If I receive 1, 2, 3, and I'm missing 4, what am I gonna do? If I receive 1, 2, 3, and I'm missing 4, I interpolate. I do error concealment. So my decoder is a smart decoder that apply error concealment. Okay? What if I lose 3 and 4? Can I still interpolate? Yes, I interpolate up down. I don't interpolate sideways. I interpolate up down because I get red and yellow, right? So I interpolate up down. Well, obviously the quality will not be as nice. But hey, you're losing half of your data. What do you expect? Right? What do you expect? As long as it doesn't look really, really bad. As long as it looks reasonably okay. Now, we actually have, I don't know if I have it in this set of slides, but my group has techniques that I lose 3/4 of the data. And you can still see that. Okay? Might not be the prettiest letter that you've ever seen, but it's okay. You can still recognize that, okay, this is a person. Okay? It's a woman, and I can tell you for sure that it's Lena, because I've seen Lena so many times already. I have my correlation, matching correlation techniques somewhere in there. So the joint decoder estimates the lost blocks from the received blocks, and this interleaving scheme can be applied directly in the time and space domain as well. Okay? If you think about the partitions for the next frames, you can try to do something similar. The entire idea is to make sure that you have data to interpolate. Okay? So this is, oh yeah, so I have this, okay. So this is the case where I receive everything. Then I receive everything. Then B, receive 3 out of 4. And then 2 out of 4, and then 1 out of 4. 1 out of 4. And just interpolate from the red, for example. And you can still get this. Barbara, This is 4 description, looks absolutely beautiful, right? 3 description, the PSNR might be low. 28 is considered low. Anything below 30 is considered there might be some problem with quality. Okay, but as you can see, good interpolation techniques will lead you to very visually pleasant image, although the PSNR can be quite low. And then, even with 1 description, it's still very clear. You can still tell that this is Barbara, not Leonard. Right? You can still see nose, eyes, and mouth, and everything. Okay. So that's another technique that people use all the time with multiple description is called the concept of nested quantization. Okay? Nested quantization means you design your 2 quantizer for the 2 description in an overlap manner. So if you only receive this description, this from description red, okay? Where should I reconstruct? Maybe in the middle of the intervals, right? So I have these red reconstructions. And if I only receive the blue, then I reconstruct it in the middle of these blue intervals, correct? What if I receive two guys? What if I receive 0, 1, and 1, 0? What if I receive 2 descriptions? So I receive 0, 1 for the first description, right? Then what? And then I receive 1, 0 from the second description. What can I say? I can say that my data doesn't belong here, it doesn't belong there, but it will belong in the overlap region. So where should I reconstruct? Middle of that interval. That is called nested quantization. Very simple idea. It works beautifully. Okay, you base your estimation, your smart estimation, based on the fact that you receive your neighbor. Okay, so this is a technique that seems to work very, very well, and it can be combined with the other techniques that we talked previously on interpolation. Okay, so transport level control, right? When you do packetization, you can try to repeat the coding modes in successive packets, so that you also have, not only you have the coding modes of yourself, but you might have the coding modes of your neighbor as well. Okay, and you repeat that information. So at least the vital information is always there for you when you try to decode. Spatial block interleaving, we talked about this already. That's the idea of having red, yellow, green, and blue. You never have neighboring blocks grouped together in one packet or in one description. You always try to separate them out so that when you lose something, at least you have a chance of interpolation. Okay? And finally, you have things like interactive error concealment. And this is the most advanced. Okay? When you involve both encoder decoder. Okay? You have retransmission without waiting. You have multiple copy retransmission. We have selective encoding. Those are techniques that involves a lot of interaction between the encoder, decoder, and the channel in order for it to work. Okay. Finally, let me just say something really quickly about error resilient redundancy. Okay. Now this is everything we do is at a trade-off. Okay, it's a trade-off between compression efficiency versus communication bit rates versus bit error rates of our lossy channel. Okay, so if there is no error, the green line indicates the video quality with respect to redundancy level with a green line right here. Okay, when there is no error, okay, highest video quality is achieved when you have minimum amount of redundancy, when you have zero redundancy. Is that correct? So this is the case of pure source coding. Right here, this point right here is the absolutely highest video quality, the highest video quality level is achieved when you do not have any redundancy in your channel codes. Okay? Because you don't need any protection, right? There's no error. We don't need any protection, so we don't waste any bits. All the bits go to compression. Okay? Now, but then when the channel error increase, for example, yellow means you start to have a reasonable amount of channel errors. Okay? When you have a reasonable amount of channel errors, you don't protect anything, you don't get optimal result. The optimal result is right here, where you actually have a certain amount of redundancy added to your for protections. Okay? Now, what happens when you overprotect? When you overprotect, you reduce the quality because you don't have enough bits for compression, right? Because everything is based on a fixed given bit rate, right? So on a fixed given bit rate, you overprotect, you don't have enough bits for compression, so your quality go down. Okay, right at this point is where you put everything toward protections and you don't have any bits for compression. So this is also very bad. But then when you have a lot of errors, certainly you have a lot more protection. And now you also should notice that there's a curve, there's a line going down. The line is going down. Notice the best performance is here, the next best is here, the next best is here. Okay, the level is not the same. Okay, because for a fixed communication bandwidth, and if you spend bits on redundancy protections, you don't have bits for compressions, and there's no way you can compete with the green line. Okay. So the line will start moving this way, and the peak will be lower. The peak will be lower all the time. Okay, and at a certain level, there's just nothing more that we can do. When the error, when the channel is so lossy, then maybe we should not even consider communicating over that communication channel. Because there's just nothing we can do. Okay, so let's summarize. Okay, these are the techniques that people use in error-resilient image video communications. Obviously, the quickest and easiest thing to do would be just to retransmit the data, repeat the data. And that is very bandwidth inefficient and delay, outrageous latency in delay. Okay. Next, we talk about forward error correction, which is the channel codes allow us to provide protection for our bit streams. Then we talk about error concealment, which is a technique that allows error to occur, but try to go back, revisit the location of the errors and try to conceal. Okay, try to hide it away by doing smart interpolation. Okay. Finally, error resilient video coding involves combinations of many of these things. Okay. We need to resynchronize, we need to limit error propagation, and we need to investigate smarter techniques like scalable video coding and multiple description coding. Okay? Now, I only have 15 minutes left, so let's say a few things about multimedia streaming over internet and wireless networks. Because this definitely will be one of the areas where research is still being done every day and might have a tremendous impact in the near future. Imagine that you can communicate with everyone on your cell phone, okay? Not only voice-wise, but also video-wise. Like we can do real-time video conferencing using cell phones, okay? It's probably not available in Vietnam, right? It's not available in the US either. But there are a lot of people working here, and some of the slides come from them. So this is my courtesy slides. So maybe I will only have time to cover some of the history, the motivations, and maybe tell you a little bit about the fundamental problem, okay, that we are facing with streaming. Okay, so let's streaming media is actually a huge success within the last 10 years. There are hundreds of thousands of streaming media servers being deployed. Okay, more than 1 million hours of streaming media content produced per month on the internet. Okay, so every video that you watch over our DTV website is in streaming video format, right? You click on it, and you're gonna wait for a little bit at the beginning for buffering, and then the video start to play. Okay, real players and Windows media players are two popular software that allows you to do streaming media. So the most popular internet application, second only to Internet Explorer, turns out to be real player. More than 400 million unique registered users for it. Okay, it adds about 200,000 new users per day, and it has open source. If you look hard for it, you will find. Okay, so it started somewhere in 1992. Okay, and then let's see. In 1997, Real Video or Real Network becomes a public company, and they keep on buying all these small guys, Sings and Vivo, and becomes a major player. Okay, in the year 2000, it reached 100 million users, but then the internet stock market bubble burst. Okay. So Real Network go all the way down the sink. Now, in 2000, but it doesn't mean that the company is going away. It's not just growing as rapidly as before. Okay. But then Microsoft decided to enter the game, so it started to compete with Windows Media, and now I think they are sitting at Windows Media 10, right? Okay. The latest players that they have is Windows Media 11 now. Oh, I'm way behind you guys. I think I'm still using Windows Media 9. Okay, in 2006, Single Wireless, which is a major player in the wireless area in the US, actually provides on-demand streaming video services to that user. You have to pay. Okay, but it's there and it's available. And Windows Media 11 Polaris should be available for you guys. So this is the problem. We have the media server that typically go through the internet channels. Okay, there are many people accessing this media server. Okay, they might have very high-speed ADSL line. Okay, like your regular desktop setup. They can probably not a lot of people doing 56K modem anymore, but still there might be some. There are people accessing it from their wireless cell phone, for example, or their PDAs. Obviously, we have to worry about compression, scalability, error resiliency, low latency. So all these things has to come into play. Okay? Now, so we understand all these already, so let me skip. Okay? Now, typically, the architecture for media streaming is shown here. You have the streaming server, which is where Akamai sits, where Real Networks and Windows Media sits. Okay? And it has raw video coming in, raw audio coming in. It has a storage device with the encoder built in, so it will do encoding, store it in the servers. It has application layer, quality control stuff over here. Transport protocol, like the one that we talk about, packetizations and headers, information. So it has all these. Okay. The output is going through the internet wireless IP networks with internet protocol. At the receiver, you have the transport decoder, and then you have the application layer QS control, which might do concealments and all these error detection correction stuff. Okay, and then it has the video decoder, audio decoder right here with synchronization and playback. Okay, so we talked about video components already. So maybe the most important things in here is the application layer quality control, because that's where so we're very familiar with all this. Okay, we know what this is doing, we know what this is doing. So the rest is just good. Okay. Now, so in streaming, media stored at the source, right here, it will be transmitted to the client through all these nodes, okay? And the client playout, which begins before all the data has arrived. So the key word here is before. Okay, this is where the difference between streaming and downloading. In downloading, you hit the download button, you wait until everything gets to your desktop, and then you play. Well, okay, then you just wait, okay? And there's no challenge there. Okay, the challenge is the client starts to play before the data are dry. So what it means is maybe there's a buffer at the beginning, okay, and the key is to reduce the buffer, right? Reduce the wait time. And ideally, you would like for the client to play immediately when they hit the play button. But most of the time, that's not achievable because we don't have the communication bit rate. There's a lot of latency out of these nodes. Okay. And now, one of the so you have the this is the cumulative data right here, and this data with respect to time. And as you can see, the data, okay, the draw data coming in being compressed, okay? And these are the size of the video that start to go up, okay? So the size keep on growing, the size of your entire video that you are about to send. For downloading, we're going to wait until the video is completely compressed, and then we're going to hit the send button, and then you're going to wait until all the things get here, and then you play. Okay? But for streaming, what happens is you send the video like this, but then you start to play. See? You start to play right here, where all the data hasn't gotten there yet. Okay? And this is called the network delay. Okay? This is the delay between you hit the play button and the actual playout start to the first frame start to appear on your computer monitor. Okay, so the goal is to reduce that. Okay, so at this time, the client play out early part of video while the server is still sending later parts of the video. That's the entire difference between. Okay, so let's try to take a look at the delay jitter behavior. Okay, cumulative data is here, constant bit rate transmission. So let's make some reasonable assumptions. Okay, so with constant bit rate, you can see that all the stairs is very regular. Okay, so you can think of it as this is 1 frame, this is 2 frames, this is 3 frames, 4 frames, 5 frames, 6 frames, so on and so forth. You use exactly the same amount of bits for every single frame, and that will lead to constant bitrate application. Okay? Now, in a lot of the video that people stream over the web, like news and movies, okay, then you don't have this nice behavior. You're gonna have this staircase. Okay, iframe take a lot of bits and then and take a long time to encode. Okay, and then P, so on and so forth. Okay, so you have an irregular staircase, and what leads to a variable network delay. So sometimes a frame has more delay than the others. Okay, because of the bandwidth it takes, because of the bad routes that it chooses, so on and so forth. Okay, so so you have to work out the buffer such that at the client you still want this regular player, right? You don't want a jitter type of player. You want a regular player. Okay, 1 frame, 2nd frame, 3rd frame. So okay, so your job is to smooth out this type of transmission or streaming, so that at the playout is also constant bit rate and nice. So let's see. Streaming multimedia interactivity, meaning that not only you can stream, but you can pause, you can rewind, you can fast forward, you can push the slider bar, so on and so forth. So this is the advanced case of streaming. Okay, so it works just like your VCR. You can do a lot of things with it. Okay, you can. So 10-second initial delay is okay. 1-2 second delay until the command take effect seems to be okay. I'm willing to live with this, right? So, but that's the goal. Okay, how do we actually do this so that we can achieve a very minimum initial delay and it doesn't take a long time between the time where I hit rewind and fast forward to taking effect. Okay. So when you hit something, the server has to respond, and you want the server to be very responsive, very, very quick. Okay. So let me. I don't have much more time. Let me try to skip forward. Maybe let's just spend a little bit of time talking about the challenge. Okay. Certainly bandwidth is important. Okay. The bandwidth of the internet is time varying, so we have to take that into account. You need the rate control algorithm to match the channel rate. That is the key problem of streaming. So if you want the playout to be regular, if you want the playout to be regular, you have to be able to match the rate control of your algorithms so that the video bit rate match exactly the channel behavior. Okay, the effective channel behavior, meaning that not only the bandwidth that it allows you to do, but it's also how much error your channel has, the effective bandwidth. Okay, because all of that we have to be able to determine in real time how to control the rate of our compression so that it matches channel. Second, we have to minimize the end-to-end. You have to be able to control your buffer in a nice way so that it's not so large and it doesn't lead to an outrageous amount of delay. You have to minimize transmission loss. The compressed bit stream is very sensitive, okay? So you need smart error control to recover from the loss. So now the loss of streaming can come, the extreme, the most popular type of loss that you see in streaming would be you do not have enough buffer. So your buffer plays out is at the end already while the new data hasn't come in yet, okay? So that is one of the major challenges of streaming media nowadays. Now I have a lot of slides here. Most of them are pretty easy to understand. So what you can do if you really want to understand this problem, certainly there are a lot of information on the web. I think